The first talk will be Nick Brown, from a senior research fellow at EPCC in Scotland, and he will tell us about powering the future of high-performance computing with RISC-V. There you go.
Thank you very much. So, good afternoon. I hope everybody had a nice lunch. My name's Nick. I'm from the University of Edinburgh, but I also chair the HPC SIG. And we've heard a lot about machine learning and AI workloads, but also when we're talking about high-performance computing, scientific computing is really important. You know, every scientific discovery in the past 20, 30 years has to some extent involved simulation. And, you know, whether it's scientific computing, whether it's AI workloads, they're all reliant on big machines like this at the top, drawing huge amounts of power, requiring lots of plant like this at the bottom. And that's really the challenge we face in HPC, because we've got the ever-increasing demand for more performance, but yet we need to clean up our act. We need to be more sustainable, less energy while we're doing it. And I think when we talk to the HPC community, this message really lands. The fact that we've got the flexibility, the fact that the hardware can be specialized, and we don't need to rely on what just a few vendors will provide to us. But also the community-driven nature is really, really important. For many years in HPC, we've talked about co-design. And some of you might disagree with me here. It always strikes me that the ISA level is a bit like a hard barrier. You just can't get any deeper in and can't get through it. And it also seems to me that the vendors often play lip service to what we're saying. But the fact that we've got an open ISA, the fact that we've got this openness of working, certainly from my perspective, it seems that we can go a lot deeper, work a lot closer with those vendors, and actually produce solutions more specialized, more performant, and more energy efficient. Now, in EPCC, what we've been doing is standing up a testbed for high-performance computing. We're not the only ones. Barcelona have done a great job doing this. E4 have, and you're going to hear from them in a couple of talks' time. But really, the idea for us was to make it as boring as possible to the HPC community. It just feels like any other supercomputer. And actually, I was really impressed how far we could go in terms of the tools and the packages that are available already. But of course, the challenge here and the nuance here is just because it's available doesn't mean it's optimized. And what really illustrates this is this table up here. This was from a couple of weeks ago. I looked at our Cray supercomputer in Edinburgh. This is the UK national supercomputer, x86. And I looked at all the usage, and for all these applications, which of these are supported on RISC-V. And what I found is for the machine time overall, about 28% of the machine time are by applications which run on RISC-V. This is a bit high, about 35% if you ignore the unknown category. And about 55% of the users on the machine, their codes would run on a RISC-V computer. Now, I'm not sure exactly what I was expecting here. I'm not sure if those are good numbers or bad numbers. I think the 55% was higher than I anticipated. But when we were chatting about this in the HPC SIG, of course, the next question was, well, how do you define supported? You know, is it really enough that the code will just run? Do you need it to be actively maintained and optimized? And of course, that's where a lot of the challenge lies in terms of bringing these communities in and keeping them involved and showing them why they should invest in this technology. Now, like many people, when we first set this up, getting hardware was a real challenge. And we're working on these little system-on-a-chip boards. And so the SG2042, about 18 months ago, was really a game-changer for us. The 64-core part, really for the first time, a serious proposition for the HPC community. Now, the results you see on this slide, this is from NASA's Parallel Benchmark Suite, and this represents computational fluid dynamics workloads, which are really popular in HPC. And the table at the top right, what we did is we took sort of 5 of these kernels, and these numbers are averaged over them, and we compared a single core of the SG2042, so a single C910 core, against a single core of the other technologies that at the time were in our testbed, and that's these middle rows here. And what you can see is core for core, it's actually pretty impressive. This SG2042 against these other technologies doing pretty well. And also more newer technology, the bottom 2 entries for the SpaceMIT, again the C910 core is pretty impressive here. And this surprised me because obviously those last 2 have RVV 1.0. Now, what we've got on the bottom is comparing against other architectures, and now we're on all 64 cores of the SG2042. At the far left, this is a compute-bound workload. And thanks to E4 Computing for Access, their dual socket system here for the SG2042. So we've got 64 cores per socket, and 2 of them. And what you can see is really core for core, this tracks the Marvell Thunder X2 very, very closely. But the difference there is, again, that was dual socket, but just 32 cores per socket. A Skylake from a few years ago, core for core faster, but the increased number of cores really makes a difference. And then we're a little bit beneath the AMD EPYC. It's Rome, but it's what's in our Cray supercomputer there. But I was really impressed, actually, by this thing on the left. Where it starts to unravel is these other performance numbers, because these are memory bound, so latency bound or bandwidth bound. And again, black is the SG2042, and what you can see is it really does struggle much more for these workloads. And unfortunately, that features quite heavily in HPC. So from an application perspective, really this is the Achilles heel for HPC for this CPU. And obviously they've designed it for server workloads rather than HPC workloads. It's currently the best we've got, I would argue, for RISC-V in HPC. It's got us a long way, but a big message to the vendors is we're ready for the next step. We're ready for what you've announced and talked about already to be available and make it available to the HPC community. Now, this is obviously hardware. On the software side, in terms of the tooling, as I say, it's surprising what's already available for what we need. Big gap, though, are performance profilers and debuggers. Utterly crucial in HPC, very rich on other systems, and we're really missing this for RISC-V at the moment. So this is a big area of priority. And looking at building supercomputer systems out of this technology, scaling out, again, another big thing we need to focus on are parallel file systems. Things like Lustre, which is open source, it's probably quite a quick win. But certainly technologies like that are absolutely necessary if somebody's going to actually build big supercomputers out of this. And networking, we've got Open Fabric, so in theory, a lot of this high-performance networking should work. Anecdotally, people will say, well, I've done that technology or done that technology, but we need to formalize this and measure this and bring the vendors on board. And again, with GPUs, NVIDIA and AMD GPUs, anecdotally, people are playing with this and seeing some challenges, but we need to connect with this a bit more closely and think about how that links in with the server specification. Now, if I was giving this talk about 18 months ago, I'd have finished there. But what's come out in the past 18 months, past 12 months, and we see them on the show floor, are RISC-V-based accelerators, PCI Express accelerators. And I find this hugely exciting because it's a different proposition. All I need to do is get this RISC-V accelerator, put it into an existing system, and I don't need to change everything else. I don't need to worry about all the other software ecosystem, the networking, the parallel file system. But this flexibility is key here, and we'll see some examples on the next slide. What we're seeing at the moment is we've just got to take what NVIDIA and AMD give us. And to be honest with you, they're optimizing for lower precision floating point, for higher precision we need in scientific computing. Actually, the performance improvement from one generation to the next is nowhere near as great. But with the flexibility of RISC-V, actually, this is a serious proposition. And these are some of the accelerator cards that I find very exciting. This one on the bottom right by an Indian company. For many years in HPC, we've talked about posits, which is an alternative number representation to floating point. We've never had a physical implementation of this. So what they've done on their accelerators, they've taken RISC-V CPU cores and coupled this with posits. And we've got that now. Great, we can play with it. In the middle, Inspire Semi, this is coming out later in the year, and they've designed this ground up from day one for scientific computing. Not just things like the precision, but also supporting the technologies, the way in programming it to make it as easy as possible to use for the community and scaling up then from the thousands of cores on a card through lots and lots of cards. The far left, Esperanto, lots of small cards on a chip and then scaling the chips. Dave Ditzel at Supercomputing last year announced their next generation is going to have FP64 support, and that's actually a picture on the show floor of supercomputing where you could buy their cards. Again, they scale up. And then lastly, TENS Torrent on the top right. Well, we heard from Wei-Han this morning, and they've got the booth out on the show floor. And very, very briefly, to deep dive on that, what they do on TENS Torrent is they decouple the movement of data from the compute. So each of these 10.6 cores, we actually have separate embedded RISC-V cores, and we have individual kernels for these. And a lot of our workloads in HPC are some degree memory-bound, and actually this is potentially very exciting because it's this specialization that we could potentially pick up some of this performance that we might not be able to address on other architectures. Very briefly, we've played with this for quite a while. Stencil-based workloads on their previous generation of chip, with some of our benchmarking, comparable to a 24-core Xeon Platinum Cascade Lake, 5 times less energy, and a lot cheaper as well. We're currently working heavily with FFTs, utterly crucial in HPC and a lot of other places. Still some more work to do, but about half the performance of the 24-core Cascade Lake, but again about 5 times less energy. So we're really winning on the compute power per watt, and I think there's quite a bit more overhead that we can attack in terms of the performance and bring that closer as well. So, as I say, this is something that really excites me here, and we can put in today and get going with in terms of supercomputers. Now, the very last thing I want to talk about, just before I run out of time, is engagement from the HPC community. We've done a huge amount of work here in the HPC SIG, holding workshops, panels, BOFs, at big HPC conferences. Thank you to everybody in the room who's been involved in that. A little bit of a sales pitch. If you're at ISC next month, we've got a workshop there. Andrea is giving the keynote, and we've got some fantastic research talks, and also a call for papers at the workshop at Supercomputing in November. And one of the things that we've got to be careful of here is there's a fine line between advocacy and being a zealot. And so we've got to navigate this very carefully to avoid losing credibility in the community. And lastly, thank you to Andy, especially Matthew in the marketing team, for setting up the HPC presence on the RISC-V website. So just to come to a close, the flexibility provided by RISC-V really, I think, is hugely beneficial. Whether it's accelerators, whether it's CPUs, there's a lot of very exciting hardware, not just now, but coming in the future. And I think it's absolutely crucial we as the HPC community adopt this to address some of the challenges we face. But equally, it's crucial when that hardware is there, we're ready in terms of everything else. We're doing a big bit of work at the moment on the gap analysis. It's there. If you want to contribute, please give me a shout. Please have a look. It's great to get the community involvement and engagement and get a wide load of views on that. So thank you for listening. And if there's any questions, if there's time, I'm certainly happy to answer them.
Okay, so any questions? We've got time for one question.
Okay, thank you for this presentation, and I'm also excited for adopting RISC-V in HPC environment. However, there is this problem of this software portability. The NVIDIA doesn't sell its GPUs because of the GPUs, it sells because of the NVIDIA. What's your take on the RISC-V? Because you've shown a lot of different, let's say, cards that runs on RISC-V with a different architecture. How do you port all the software on these cards?
Yeah, I mean, it's a really fantastic question, and I think it's something we as the community really need to think about in depth. You're absolutely right. You know, NVIDIA has huge teams working on the software side, and that's where the real value add is. You know, even going down to the individual package level and optimizing it. Certainly, when we've looked at these cards, there is quite a lot of technology-specific stuff we need to do, and the higher question is, what can we tease out? Not just in terms of the methodology, but what can we also tease out into the compiler and how people drive this from the HPC codes that they currently have, a lot of which are in Fortran. So it's a really good question. Unfortunately, I don't have a good answer to it, but it's something we need to think about as the community and look at RISC-V where the touch points are and collaborate, because individually we can't compete with NVIDIA, but as a community I think we can, absolutely. Thank you.
Is there one other question?
Hi, Nick. Extremely interesting work. Now, let me challenge you. What is your wide-ass guess of when we will have a RISC-V environment able to compete head against head with the latest standard technology, x86 or NVIDIA? And I won't take you for that in the next years.
I must admit, I've been extremely excited about the hardware announcements that have been made, and some of the performance that's projected. But I think it really does depend on the vendors here. I would hope in a few years' time, but it might not be that we're competing on the main workloads. It might be that the accelerator cards are picking up the workloads that we can't run on current generation technologies. Actually, why would we adopt RISC-V? What was the problem it's solving that we can't solve with the current technology? And that's really where we might start to see some very special things coming in here. But it's a very good question, and I've not given you a specific answer, because I don't want to be a zealot.
Okay, thank you. Let's thank Nick again and, for his presentation.
Thank you very much.
Thank you.